Okay, guys, here's part 2 of the lecture for today, and there is an assignment that accompanies this one as well. This one is motion of a system of particles here. As soon as we can get our focus in, because this camera is really bad at focusing. Oh, almost had it. Almost there. Oh, okay, there we go. So, motion of system particles. So, let's say we've got a whole bunch of particles just flying around. You'll find this with like stars or ideal gases, and we have these particles, and say this one's moving in that direction, and this one's moving in that direction. This one's moving that way. This one's moving, up kind of like that, and this one's moving over there. And let's maybe put another one that's going that way. So we have these particles that are moving all around. Ideal gases do this. We can study the individual motions of the particles. For ideal gases, we use that a lot to determine pressure or temperature of something. But the same idea is also for star clusters. So you kind of find it. I find it interesting. A lot of our most theoretically applicable systems are either really, really small or really, really big. And here in real life, that we don't get to use a whole bunch of. It's not as pure as those situations. I've always found that interesting. Now, the first thing we want to do if we're going to find the motion of a system of particles is we want to find the center of mass. So we're going to find the center of mass. Well, just as if all these particles were differentials of a continuous piece of material, the center of mass for all of these things is still going to be, it's the average, so it's x m I x I over total mass, but then we convert that into our position of center of mass is going to equal 1 over the total mass times the integral of r dm. RDM, right? Well, actually, that's the integral of it, but that's instead of jumping straight to the integral, it's really going to be 1 over mass times the sum of all the individuals, because if it's a system of particles, then we're really counting all of the individuals. So it's going to be our sum of r I mi as I goes from 1 to infinity. Now we can have a system of particles. We can have a system of particles where our center of mass is actually stationary, but all the particles are still moving. Okay, we still have all these parts flying around, but the average center of mass can actually still be in the same spot. Okay, so in this particular case, is our center of mass? That's the question we're going to ask: is the center of mass moving? Is our center of mass moving? Okay, and so we're going to expand this term a little bit, and we're going to get our RCM is going to equal 1 over big M times M1R1 plus M2R2 plus M3R3 plus ... Okay, we can go on forever to MNRN, so however many pieces we have. And that's going to be the position of our center of mass, but we want to see if it's moving. And so we're actually looking for the velocity of the center of mass. But what is velocity if nothing but dr of our center of mass dt? And so what we can then do with this is, if we're going to find all of this, it's going to be the velocity of our center of mass is going to equal 1 over m times our mass 1 times the velocity of the first one plus the mass of the second one times the velocity of the second one, plus and so on to m n vn, right? to our nth term. But what is this velocity right here? But it's really just the time derivative of r. So we take the time derivative of r, dr dt, and that goes into our velocity right there. So so this becomes our. But what are each of these? Well, m1v1 and m2v2 and mnvn, those are all the momenta of each individual thing. And if we multiply both sides by our mass right here, if we get rid of that times m, that the momentum, so the total mass times the velocity center of mass, which would be the general momentum of the entire system, is really going to equal m1v1 plus m2v2 plus and so on to mnvn, which is really just the sum of the momenta of each center of mass, right? The sum of each one of them. So this becomes, so this becomes the momentum of the center of mass equals the sum of the momenta of each of the individual piece right there. Now, this then becomes a rather powerful statement here, because the momentum of the system is equal to the sum of the momentum of all of its particles. Okay, but what happens if we take the time derivative of our momentum? This, of course, is our definition of Newton's second law. This is what Newton did, and he found that if we did dt of this, we get, well, if it's the center of mass, then the time derivative of our center of mass really just winds up being the net force on the object, because that equals the sum of the forces on each individual object. All right, now, if there is no external net force, okay, so what if there's no net force? If there's no external force, then the sum of the momenta, okay, is going to be constant. All right, so this analysis here allows us to treat massive particles as a single particle, or huge numbers of particles as a single particle if there's no external forces. So the example I want to give you guys is, well, there's a couple. They're kind of morbid, so the first one we're going to talk about is, well, it's probably the most morbid part of our national anthem, which some of you guys know is near and dear to my heart. The rocket, the bombs bursting in air is an interesting physics problem, actually, because if we launch a bomb, or say an exploding cannon shell of mass m with initial velocity 0, it's going to follow a trajectory. Okay, if we're trying to hit this target right here, so that's our target. Well, if the bomb's bursting in mid-air, because this thing blows up right here, okay, we're going to start getting shrapnel all over the place from this bomb, and it's going to start exploding, and these various layers of explosions, and it going out. But what happens, however, is as all these individual pieces, some are going that way, some are going that way, some are going up, some are shooting out forward, some are going straight into the ground, that if we were to track all of these, okay, what is the net force on the shrapnel? Well, all of them are experiencing a similar force, because at every single point there's mg, 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 but right here it still experiences mg, right? But that's acting on the center of mass of all the particles. Well, if this is an internal force that happens, an explosion of a shell is most certainly an internal force. This whole thing is going to erupt, and all of these particles go flying, but the center of mass keeps traveling along the same trajectory. So you get this debris field around your target. So if we were to look at this from an above, okay, and there are enough. So here's, well, let me get to our interesting thing here. It travels, and here's our target. Well, it winds up that there's a debris field all around. And it's usually kind of elliptical. Okay, and that would be our, if this thing exploded right up here, okay, it has this velocity going that way, but we have pieces that are still exploding everywhere and popping up and shooting out. But the momentum of the center of mass remains the same.
There's a Fashion Club meeting
Okay, so
right now in the counseling
let's
center.
say
Fashion Club is meeting right now in the counseling center.
so let's say we have two trains, because if there's one thing that a physicist likes as much as a crate, it's a train. Okay, so we've got these two trains, and one, here's the wheels of the train. Okay, and this one has here's its end of its coupling system, and here's the other train's coupling system. Okay, and they're on their rails, and they both have a velocity. Now this one has a greater velocity than this one. Okay, and if they're both moving, then let's say this is our center of mass. Well, and let's say this is slightly heavier, so M2, M1, and M2 is greater than M1, and so our center of mass of the system is right about here. Well, if these are both moving, that means the center of the mass of the system is also moving. Okay, so, and even when they collide, because this one's going to catch up to that one, when they collide, okay, the velocity of the center of mass is going to stay the same. The center of mass is going to stay the same after they collide, okay, because the collision doesn't affect the center of mass. Okay, it doesn't affect the velocity of the center of mass, it just affects the mutual velocity of the two particles. So what we get is the momentum of the center of mass initial, okay, is equal to the momentum, I'm sorry, not M, no, not M, is equal to the momentum of the center of mass final after they collide.